We are going to pick up where we left off, and we're going to use these examples over here at some point today. Yesterday, we talked about this idea of distance and displacement. Okay? Distance and displacement. And today, we're going to talk about the use of what are called vectors. Okay? This word does not appear in your notes, but I want you to write it on this slide. Okay? Write it on this side. The word is here, vectors. Right here. It is a crucial word. Physics is founded on the principles of motion. And how do we describe motion when we draw pictures? We use vectors. Vectors are arrows that represent actual numeric or number values. Okay? They can represent direction, which is the whole point of an arrow, and they can represent a number. Okay? Now, the arrows I have up here today, okay, represent distances. They represent distances. All right, take a look at this first box over here. Okay? Event 1 is how many miles? Erica? 5 miles. Event 2, Connor, is what? 1 mile. Why are the arrows different lengths? Colby? The distance the arrow represents is different. Why isn't this one 5 miles and this one 1 mile? Why can't I switch them? Emma?
Because 1 mile is shorter than 5 miles.
The arrow has to represent the number value. It doesn't have to be 1 inch or 1 meter, but if I say this is 5 miles, this arrow being 1 mile has to be what length? Has to be shorter. It actually has to be 1/5 the length. 1/5 the length. So it couldn't even be half, because that would be representing how many miles? 2.5. It has to be 1/5 the original if it's going to represent 1 mile. So they have to be what's called to scale. Okay? If this is 5 miles, then this arrow being 1/5 the size of this one would have to be 1 mile. So if I had 5 of these and I added them all up, it would equal 5 miles. Mackenzie?
Why can't it be like on charts when you can have like a bar this big and it's only 1, or you can have a bar this big and it's like 50?
On the same chart?
Yeah.
Or different charts?
Like different charts.
Well, that's fine.
The length of the 5 mile arrow, and you could only have like 1 mile, and then you could have the length of the 1 mile for 5 miles.
So I'll give you an example. Look at that 1 mile. Look at this 1 mile. See how much shorter it is? Okay? These are different examples. So we're only working within the realm of a single example. I could draw an arrow that represented a mile, and it'd be the length of my board. But then if I wanted to represent one in that same example that was 5 miles, I'd need 5 boards this length to then draw that arrow. Okay? So I have to work within my example. So on a graph, some bars represent little numbers, and then on another graph, a same size bar might represent a much larger number, but they're different graphs. And so that makes a difference as well. Okay? And these are the kinds of things that are really good to ask. Okay? Good questions. Feeding the teacher. All right? I'm hungry, and yet I get these good questions, my bread and butter. All right, so I have event 1 and event 2. What do I mean by event 1 and event 2? Do they happen at the same time? Well, if I were wanting them to happen at the same time, I might say event 1 and event 1 and say that they happen simultaneously. Okay, by specifying event 1 and event 2, what am I saying? Yeah. They happen at different times. Okay, and you'll see this a lot. You'll see us working from the top to the bottom. So usually things that happen first are at the top, and things that happen second at the bottom. Okay? Yes?
Okay, so what would you do if you like switched them? Let's say you had 1 mile, and then you had another one that said 4 miles. So in total you did 5 miles, but you stopped after.
I could do that. I mean, so in event 1, because I have one continuous arrow, okay, it means that I went 5 miles in one trip. But I could have also gone 1 mile, and then, so I'll just put a 1 mile. And I could have also have gone 4 miles, and I could say these are event 1, so I'll just put E1, E1. Event is specified by a start and stop time. Within that start and stop time, things can happen. Okay? So what happens here is we see we went 1 mile, and then there's possibility that we stopped, and then we went an additional 4 miles. So event 1 could be represented by one continuous 5-mile arrow, or 2 arrows that are both within the event 1 category, one for 1 mile and one for 4 miles. Okay? So Reagan's right. We could represent it in different ways. We might see things like this. Somebody goes a mile, then they go 4 miles. Okay? And then a little while later, for event 2, they go an additional mile. Okay? Now, when we have different events, they're often stacked like this. Okay? And usually what ends up happening is we want to combine them all at the end. Okay? If you look at the board up here, this is called adding displacements. These are displacement vectors. They're vectors because they represent direction. So I can add them. So if you look up here, there's some key components. First of all, they're arrows. I love arrows. Love them. Arrows tell us where and we are going. They tell us direction, and they can specify size. So here I have a 5 meters east, and then like Reagan's example where we have 2 arrows that are next to each other, an additional 5 miles east. And when we add it all up, okay, adding them all up, the laser pointer does not work on this screen, it's a total of 10 miles in the easterly direction. Okay, so, and write this in the notes next to the slide, you can add vectors, or you can circle this here if you want, that are going in the same direction. Yes?
Okay, I'm confused now because you just said that was 10 miles, but it's an M, and I thought that was meters.
Oh, thank you. It is meters. 5 meters, 5 meters, 10 meters. My bad.
I wasn't sure, and I didn't.
No. That's a very good thing to specify. If you hear me make a mistake like that, please clarify. Absolutely. 5 meters east, 5 meters east, 10 meters east. Absolutely. If it was miles, it'd be a little mi. Meters is a little m. That's a very important distinction. I appreciate the clarification. Mackenzie.
If you can add them in the same direction, do they have to be almost touching like that, or can they be like way far apart?
No, they could be far apart, or they could be like this, where event 1, the black arrow here's here, and then event 2 is here. So we notice event 1 we went 5, then in event 2 we went 1, so we would say they went a total of 6 miles. Okay? We are adding event 1 and event 2. Notice they're not next to each other. Notice one's on top, one's on bottom. That's okay.
So they could even have like a gap. I mean, that's the same thing, but like event 2 is 6 miles. That big of a, like if it's the same route.
Yeah. Like this one, there are 4 different things that happen. This happens, then this happens, then this happens, then this happens. And we're going to talk about this one in a minute. But notice that I don't put them all on the same line. I don't draw one arrow this way and then another arrow pointing at it. I try to specify events by drawing them like this. Really, this one should be here. That was my bad. I should have drawn this one over here. Okay. Now, we can add displacement vectors that are going in the same direction. The opposite is true for vectors that are headed in opposite directions. They actually subtract. Okay, I'll give you an example. Event 1 here, we go a full 10 miles. Stop here. Then event 2, we reverse direction 180 degrees and go back 2 additional miles. Okay. Now, we know from our discussion yesterday that we look for displacement at our final resting spot in reference to our initial starting point. So we started here and we stopped here. What we're really doing is we're subtracting that 2 miles from that initial 10. If you lay it out pictorially like this, they really are just canceling. Okay? So sometimes what I do when I'm drawing pictures of advanced systems, so I'll sometimes put the vectors next to each other and I'll just cover them up with my hand or a piece of paper or a note card. And then what we see happen is when we cover them up, we're removing 2 miles from our initial vector. What are we left with? We're removing 2 miles from 10. These are canceling. What would we be left with? Yeah. We'd be left with 8 miles. And that would be our displacement. Okay, that would be our displacement. So if you look up here, when we have vectors that are going in opposite directions, there's a canceling effect that takes place, a subtraction that takes place. So using meters, not miles, if you go 10 meters east, but then you go back 5 meters west, you are literally canceling out any motion you had made in the easterly direction. These cancel, and you're left with what is called the result of 5 meters east. This red arrow is your displacement. Okay, your displacement. Thank you. Yep. All right. Now, we have 4 events that happen here, represented by 4 vectors of different sizes in different directions on this last chart. We have 3 miles to the right, 1 mile to the left, 6 miles to the right, 2 miles to the left. Okay? Now, there's 2 ways to solve this problem. The first one that I really like is a number line. Okay, you can't go, we aren't necessarily going to go negative in this example. So we start at 0, which is our starting point, and we go 3 miles initially. Then where do I go? Millie. I go back 1 mile, so I'm going to go to 2. Then where do I go? Gretchen? I'm going to go 6 to the right, so that's to 8, and then what? Yeah. Then back 2 miles to 6. Now, what if I had said instead of 2 miles, it was 20 miles? What would have happened? Yes. Yeah, I'd be back here in the negative direction. Now, typically speaking, instead of negatives, when we're talking direction, we use east, west, up, down, left, right. But sometimes we use positive, negative. These are all ways for us to specify direction. Okay? So like in high school, when physics students are trying to analyze rocket motion, right? We talk about up as being positive, down as being negative. So when something is going up in the air, it's going in the positive direction. Something is going down, falling towards the ground, it's going in the negative direction. Okay? So oftentimes in physics, we specify with positives and negatives as well. These are vectors. Now, are they always really nice forward and backward? No. Okay, they're not. Oftentimes, especially in like mathematics and other things like planes, computer systems are meant to work in 3 dimensions. So there are vectors that are going like in 3 dimensions this way, and then this way, and then this way. Okay, and so there's some really advanced computer graphics that have to go, because all a computer can read about a plane is its position in the sky. But what goes into its position? What goes into a plane's position? Tell me. Huh? The plane. A plane is flying in the sky. What do we have to know about its position in order to know where it's at? Yes?
Coordinates and altitude.
Okay, coordinates and altitude. So what is that? Altitude gives us how far off the ground. What do coordinates give us? Huh?
The location on the Earth.
Location on the Earth. So north, south, east, west. Okay? You can have a person that's the same coordinates on the Earth as a plane. What's different? Yeah.
The plane's higher up in the air.
Planes higher up in the air. If 2 planes are coming in towards an airport, what their coordinates could be show an intersection, it could show a collision. But what could be true? They could go over top of each other, they could go under each other, they could cross paths at different altitudes. These are called skew lines, by the way, if you remember skew lines. All right, so there's a lot that goes into. Computers read direction by looking at things in 3 dimensions. And you won't do that in school. At least not in regular school. Unless you go into into some sort of engineering or physics or computer science, video game design, they have to think like this, all of that. Okay? Okay. Displacements are not in the same direction or in opposite directions, cannot be directly added or subtracted. So if they are not directly opposite each other or in the same direction, you end up with situations like this. Okay? I'll give you an example. Say I'm going to the store, but to go to the store, I cannot walk directly there. Otherwise, I'd have to go through a building. Okay? That would be a challenge, unless, of course, you're Mr. Incredible or the Juggernaut or something like that. Okay? So I have to go 4 meters east. Okay? It's a very small block. 4 meters east, 3 meters north. And then I can get to where I want to go. The thing of it is that your displacement is your distance from your starting point, not the path you took. The path I took was 4 meters and then 3 meters, a total of 7. But my displacement is a direct beeline towards where I started, okay? Which would be a grand total of 5 meters northeast. So now we're starting to get into different compass rose, cardinal coordinate system, things like northeast, southeast, northwest, southwest, etc. All right. Does anyone remember in mathematics how you would find the hypotenuse of a triangle? Yeah?
A squared plus B squared equals C squared.
A squared plus B squared equals C squared. The Pythagorean Theorem. The Pythagorean Theorem is what we would use to find displacement if I knew how far I went this direction and how far I went this direction. I would do A squared, 16, plus B squared, 9, gives me a grand total of 25. I would take the square root of 25, and it'd give me 5 meters northeast. You will have one of these for your tests. We're going to practice one tomorrow, the Pythagorean Theorem. Okay? The reason you learn that math in 7th grade, the reason you do that is because when you get to, or actually 6th, 7th, and 8th grade, it's because you'll use it in science class. I don't know if you did or not. Did you learn it brand new last year?
Yeah, we talked about the Colbert Theorem.
Okay. All right, ladies and gentlemen, that is all for today. Vectors. You will have another quiz in a day or 2 time. All right. Make sure that you're taking notes and getting notes and being responsible. And I will go ahead and end this recording and put it up online. Hopefully it worked today.